the slideshow from the current slide. All right, before we get started, we're recording. Before we start actually the math, let's go over. There were several really good questions at the very beginning. Let me hit the answers of those now that I'm recording and more people are in the room. We're going to continue with 5.2, hopefully get into 5.3. Today, 5.3 is pretty short. Hopefully we'll get it all done. But if not, I'll still give you the quiz on the first part of Chapter 5, okay? It's pretty good stuff. Y'all seem to be catching on to it well. It should give you a pretty good quiz score, okay? That will be due. If you can get it to me by Wednesday, fine. But if not, get it to me by when you come in to take the final exam, and that'll be fine. Now, that's one thing. Let's see. How many have done the student course evaluations? Okay, quite a few have not yet. Please do those. They really are important. I value them. I use them for myself. I use them for evaluating my instructors, and the college uses them to document that we're getting student input. It is really important that we get those in. Please do the student course evaluations. Okay, that said, let me also say this one while I'm thinking of it. Please vote next Tuesday, not tomorrow, but 1 week from tomorrow. If you're a resident of Alabama and registered to vote, please vote. It's one of the most important things you can do in a democracy. That's what we all depend on, is people voting, so please vote. All right, that's out of the way. Now let's talk about math. We're going, like I said, do as far as we can in Chapter 5 today, okay? And then, once we're through with today, it's Tequila, I thought so, okay. I want to mark the right person. Okay. Once we finish today, on Wednesday, we will strictly be doing the review sheets. Okay, I passed these out early in the term. A few people either never showed for the class or didn't come and withdrawn since or whatever. So I do have a few left. If any of you cannot find yours, I do have a few of these left. But please bring these with you on Wednesday. In fact, start looking at them soon, and anything you see on here we haven't done. And it starts off some stuff that, whoa, I haven't seen this before. Unfortunately, that's right on the front page. But as you go through it, you'll see much of the stuff we have done. But anything that you are uncertain about, you have questions about, then these. There's both the multiple choice part and the short answer part, okay? Any of those questions, bring those questions to class, and I'll answer anything that you have on those sheets. We'll do that on Wednesday. Then, technically, our final is scheduled for Monday, 8 o'clock in the morning, and it's an hour and 50-minute final, not an hour and 15-minute like the class is. However, I am quite willing to use that time as an additional review period, and as soon as that review period's over at 9:50, anytime after that, Monday, Tuesday, Wednesday, or Thursday, you can come in and take the exam anytime you want to, okay? If, however, you say, hey, I'm ready for the exam Monday morning at 8 o'clock, I will get someone, if the whole class says that, I'll give the whole class, the exam will be ready for you. But if any of you want the additional review day, then I'll get someone to proctor the exam, and we'll continue with the review, okay? Is that understood? So we'll continue doing those review sheets. We'll do them Wednesday. That's all we'll do Wednesday. Well, with one exception. I want to return every paper you've turned in to me, except the research paper, which, by the way, I need those in. I would say probably close to half the class has turned those in so far. This is the last week, folks. This is the last day you can turn it in without losing points. So please get your research papers in, preferably today or tomorrow, but no later than Wednesday, okay? And then if you have any quizzes you haven't turned in yet, if you haven't finished the test, please get that done before Wednesday. Because Wednesday morning, before we start the review session, I'll be returning all of those quizzes and tests to you. Not your research papers. I have to hang on to those because they ask periodically for samples of student writing, so I have to hang on to those. But all your quizzes and tests, I want to return to you then. So if you have a partial score, that's what's going in the book. I don't think you want that, so please get that done. Or if you haven't turned it in or haven't even started it, then the 0 goes in the book. I don't think you want that either. So please, folks, get with me today. And let me go over my office hours again. Today is 3:15 to 5:15. Tomorrow, 1:15 to 3:15. And then, of course, Wednesday is just like today, Thursday is just like tomorrow. Friday, I'll be on the Birmingham campus, 7:45 to 11:45. So if you are planning to come make up some work on Friday, be sure you let me know today or Wednesday so I can put it in the book. Otherwise, I'll be on Birmingham and your test or your whatever is going to be out here. That's not going to be easy to do, so please let me know. All right? All right. Have I covered it all? Aria, right? Okay. Okay. And has anyone else come in? I did not call your name. Okay. Now, let me start with this. Any questions from anything about how we're going into the term, student course evaluations, whatever. Any questions at all? Okay. If you came in and didn't catch all that, listen to YouTube. Because I go over what we're going to do the rest of the time. All right. So if no questions, we were on top of page 256, chapter 5, exponents and radical, 5.2, roots and radicals, and we were on example 5D. Okay? And I'm pretty sure this wasn't in, this is not in your, okay. There's something a bit strange today, but I'll live with it. Normally, when I do something like that, well, things are offset, and it's good. It's not bad. Simplify each of the following. The cube root of 5 divided by the cube root of 16. Where do we begin on a simplification of something such as that? Okay, 5 is a prime number, so there's nothing you can do with that. But we're not really that interested in numerators at this point. What are the 3 things that we watch for simplifying radical expressions? 3 things. I know it's been a long time, at least a weekend, since we last met. Okay, no, if we were adding or subtracting, common denominator. But it has to do with denominators, okay? 2 of the things have to do with denominator. 2 of the 3 have to do with denominators. What's that? Okay, we do not want radicals in the denominator. We got one, okay? We don't want denominators in the radical. We don't have one of those, but we have the other. And what's the other thing? Okay, we're going to do that. That's exactly what we're going to do. But what's the 3rd thing we watch out for? You don't want a perfect, in this case, cube hiding inside a cube root. Right? If you have, take it out. Make it simpler. Simplify things. Do you see any perfect cubes? You've already said 5 can't be a perfect cube. It's a prime number. But how about 16? Are there any perfect cubes hiding in 16? What? 4 is a perfect square. What's a perfect cube? 6 isn't a cube. Huh? Yeah, you're right. Let me get, this is, I know you're on, there's Justin, right? Yeah. Okay. Couldn't find you. Okay, has anyone else come in since the called roll? And again, let me say this. Anyone who came in after all the introductory stuff, please listen to YouTube because we'll talk about what we're going to do the rest of the, this week and next week. Okay? Yeah, 2, what's the cube of 2? 2 cubed. 8. Is there an 8 hiding in 16? Yes, there is. Okay, so we want to first take that out. So let's leave that numerator alone for now. The cube root of 5. Not much we can do with that. We don't really worry about numerators too much. But this is going to be the cube root of 8 times the cube root of what? 2. Exactly. And what is the cube root of 8? 2. Okay, so that's 2 times the cube root of 2. Now, okay, we got rid of one of the things. One of the things, a perfect cube hiding in a cube root. We got that out. Done. The next thing, we still have a radical in the denominator. And what Jalen was suggesting that we do was what? What we don't like is these things in denominators. So how do we get it out? Multiplied by what? Say again? Okay, not quite the cube root of 2. If that was a square root of 2, we'd multiply by the square root of 2. Perfect. But we need 3 2's in there. There's 1. We need 2 more, so we multiply by the cube root of 2 times 2? 4. If we multiply that by the cube root of 4, we have to multiply the numerator by cube root of 4 as well. Okay? Now the numerator now becomes what? The cube root of 20. Okay? There's no perfect cubes hiding in there, so we're okay. And what's the denominator now? We had a 2 there, and now we've got what? Cube root of 2 times the cube root of 4. That would be the cube root of 8. And what's the cube root of 8? 2. Okay, so we got another 2 down here. So this gives us the cube root of 20 over 4. And there's nothing we can do to simplify that. Nothing. You can't go inside a radical and divide out anything. You have to have things on the outside. Okay? That is our answer. It's sort of ugly there. The cube root of 20 over 4. And let's see what the book got. Oh, good for them. They got it right. You see it? Any questions on that? Okay, again, the 3 things we don't want to happen with radicals. We don't want a perfect net power, okay, in this case cube, inside a cube root. We had one, we pulled it out, dealt with it. Secondly, we don't want radicals in the denominator. That's what we did by getting rid of that. You have to have 3 powers of 2 to get rid of that. So we had 1 power, we multiplied by 2 more. Okay? But we had to do it to the numerator as well. That gave us a more complicated numerator, but who cared? It made our denominator simpler. The other thing, we didn't want any denominators in a radical. We didn't have any to begin with, so we were okay with that. All right, good deal. Any questions on that? All right, let's move on to applications of radicals. Many real-world applications have involved radical expressions. For example, police often use this formula. I don't know if you've ever been in an accident before that some car has hit another car, and you'll see the police out there measuring the length of the skid marks, and what they're doing, they're using a formula just like this to estimate speed of the car that was slamming on brakes. It won't give them an exact, but it gives them an estimate. And this speed, S, is the square root of 30, where that comes from, we're not going to get into that, D, okay, we'll get into that later too, little f. Little f is a friction factor, okay? D is the distance of those skid marks, okay? And 30 is just a number that fits, okay? So to estimate the speed of a car on the basis of the length of the skid marks at the scene of an accident. This formula, S, represents the the speed of the car in miles per hour, and it's just an estimate. D is the length of the skid marks in feet. That's part of where the 30 comes from. And F represents a coefficient for friction. Okay? And they'll have different coefficients if it's a gravel road rather than a paved road, rather than a dirt road. If it's a wet road or an icy road or other roads, they have different coefficients of friction. So they'll enter that as well. For a particular situation, the coefficient of friction is a constant that depends on the type and condition of the road surface, like I just said. Okay? So here's example 6. Using 0.35 as your coefficient of friction, what symbol was that from the previous slide? Oh, it was a long time ago I said it. That was your little f. Little f, that's the 0.35, coefficient of friction. To determine how fast the car was traveling if it skidded 325 feet. What was that? That was your D. Perfect. Okay? And what was the formula? We're looking for how fast. That's going to be the speed. That's the unknown here. And what was the formula? Square root of 30 df. Okay. Simple plug and chug here. 30 times 325 times 0.35. Okay. If you got a calculator, plug it in, plug it in. That'd be 975 times 0.35. It'll be something a little more than 100. Square root of that is going to be something like 10, 11, something around in there. No, that can't be right. 975 times 0.35. That'd be 3 something another. I'm sorry, 3 something another. Square root of that would be maybe 60 or so. Say again? 58. Okay. Is that what they got too? Or is that where you got it? Oh, this is not, okay. Yeah, here we go. 58 miles per hour. Approximately 58 miles per hour. Now, if that was a 25 zone, doop, that guy's got a big ticket, okay? If it was a 70-mile zone, they can't ticket him for speeding. Maybe other things, but not for that. What's that? Okay. Do you have a calculator?
Yeah, I used to do it. I got 3,402.
You got what?
3,402.
Okay.
I multiplied all those numbers.
Okay. Did you take a square root? Okay. Well, when you multiply it, I don't think you multiply by the decimal. It's 30 times 325 times 0.35. That's going to be something on the order of 300. Okay. And then you take the square root of it. Okay. Oh, okay. Oh, that's fine. Okay. All right. Let's start over. 30 times 325 times 0.35 equals. Oh, okay. I was messing that up, wasn't I? And then you do. Oh, you don't have a square root key. Okay. Okay. I'm sorry. The my phone, when you turn it over, you get a better calculator. But I have my wife's old iPhone. But you need a square root key. Okay. So, which is a good point. I'm glad you brought that up. Please, folks, on the final exam, you'll probably need a calculator. Bring a calculator. I used to have a little stash of calculators. They all died or got walked away or something like that. So I don't have them anymore. I have one that I can remember works anymore. The rest of the batteries have died or whatever. I'll bring that up and let someone use it. It's not a very good one. It's a cheapie, but it will do square roots. But please bring your own calculator so I don't have to show you how to operate a calculator. Learn how to do your calculator. Bring it for the final exam. It will be helpful. Please bring it. Okay, that was example 6. Oh, let me clear this. All right. Oh, got it. Andrea. Okay. Does anyone else come in? That's Chuck, right? Okay. Let me clear the screen. Okay. And here's how they did it. S is equal to the square root of 30 times 325 times 0.35, which is about 58 to the nearest whole number. Car was traveling approximately 58 miles per hour. Okay? It could have been in excess of that, more than likely was, because if it hit something, then obviously it didn't have its full skid mark. So that's all they can prove, that it was going at least 58 miles an hour. All right, here's another example. Okay, now for folks who have just recently come in, let me say this again. Be sure you listen to YouTube for this class, because at the beginning of that, I went over how we're going to wrap up the class. So please listen to that. If you have any questions, ask. But don't want to go through all that again. We need to get as much covered as possible. Here's another application of radicals. This is, by the way, on page 256, Chapter 5, Exponents and Radicals, 5.2, Roots and Radicals. A period of a pendulum, that's a good old cuckoo clock, grandfather clock, whatever, is the time it takes to swing from one side to the other and back again. That's called the period. And the period is represented by capital T. Okay, you might say, why period T? Well, it's a time. The time it takes. So that period, the time of the period, is 2 pi times the square root of the length of the pendulum, that's the L, divided by 32. Now, I'll tell you this time exactly why 32 is in there, because you're dealing with feet, and the acceleration due to gravity is 32 feet per second squared. That's where that comes from. You don't need to know it, but that's why that's in there. It can be used to determine the period of the pendulum. All right? So there's the setup. Let's see if they give us a problem with it. No, they didn't. Okay, so let's us do the problem. It says, find to the nearest tenth of a second the period of a pendulum with a length of 3.5 feet. So here we're going to have the length of 3.5 feet. Okay? So basically, 2 pi times the square root of 3.5 divided by 32. Now, if I wanted really to be thorough about it, I'd put the units in there. You don't have to just use the formula. It works. But just make sure if you're using 32, that length is in feet. And I think most of the time it will. So if someone's got a calculator, this one will need a pi key on it. Can anyone do that on your calculator? 3.14, yeah, 3.1416. If you wanted to use that, you can do that. If you don't have a pi key, you can do that. But you'll still need a square root key, which you didn't have before. You still not have it? Okay. So please bring your calculators to class for the test. Anyone got one that you can do this? Everybody's really excited to do it. Does anyone have a calculator that will do this operation? Folks are going to be hurting badly if you come to the final and not able to do a problem like that. Has anyone got a calculator? Okay, good. What you get?
No, I'm saying like I found
Good.
the scientific.
Okay. What you got? I was still putting it in. Anyone got it in yet? I would think most of the smarter smartphones have that somewhere. I just can't tell you how to find it on every one. Any answers yet? Okay. Okay. Now it depends on how your calculator works. If you want to do it the brute force way, 3.5 divided by 32, take the square root of that and then multiply it by 2 pi. Yeah. Yeah, after you divide it, take the square root. Okay? Now, some calculators don't like doing that. They like you to do 2 pi radical, open parentheses, 3.5 divided by 32, close parentheses, equal. Yeah. All right, let's see. Yep, they said to the nearest tenth, so that would be about 2.1 seconds. Perfect. Okay, and that's what they got in the book. Good deal. Now, this is the verbiage, the paragraph right below that example 7. Radical expressions are also used in some geometric applications. For example, the area of a triangle can be found using a formula that involves a square root. Okay? This is called Heron's formula. If any of you continue through trigonometry, you'll see this again. If A, B, and C are the lengths of the 3 sides of any triangle, it doesn't have to be a right triangle, any triangle, then the formula K, where they came up with K, I'm not sure, but this is the area, is the square root of S times S minus A times S minus B times S minus C. Okay? What in the world is S? S, and that's Heron's formula, the whole formula is, it can be determined, the letter S represents the semi-perimeter. Okay, Jay's here. Okay, I know you're on the roll. There you are. All right. Good deal. Does anyone else come in since I called roll? Okay. S is the semi-perimeter. What you do is take the 3 sides, add them together, divide by 2. Okay, you're not averaging, it's say half the perimeter. So add them together, divide by 2, that's your S, and then plug that in and go from there. All right, so let's see if we can, whoa, they didn't give us a one to use that. So let's do it here. Example 8. Okay. Find the area of a triangular piece of sheet metal that has sides of 17 inches, 19 inches, and 26 inches. Now, I don't know if that's anywhere close to reasonable. We want the area of that triangular piece of sheet metal. So what's the first thing we do? Say again? I can't hear it. I hear you say something, but I can't make it out. My hearing's good. Okay, add them together. Okay, so 17 plus 19 is 36, and 26 is 62, right? And divide that by 2 and you get 31. So your S is 31, semi-perimeter. Now they use the symbol K, I would use A for area, is equal to the square root of 31 inches, that's your S. Now multiply that by S minus A, and let's just call this one A. So that would be 31 minus 17, that would be 14, right? That's also would be inches. times S minus B. Let's just call this one B. S minus B would be 12 inches, right? And then our final one was C, and S minus C would be 31 minus 26 is 5. Square root of, multiply those together. And to me, the easy way to do this, these two multiplied together would be 60. And yeah, it still would be hard. So just deal on it with the calculator. Square root of 31 times 14 times 12 times 5 equal. Someone give me an answer. Say again? Okay. Did you take the square root of it? No. Okay, take the square root of it. Ah, excellent. 161.4, and that would be square inches. There's one symbol for square inches. They write SQ, well, they spell it out, square inches. Yeah, but you take the square root of that. But your multiplication was correct, square root was correct. Now, how to guess, is that about right? Well, I'm just going to make an estimate here. If this is your base, there's your height. I'm just going to say the height, let's just say 10. It's probably going to be less than 10. So 26 times 10 would be 260, and half of that would be 130. Not far off, okay? That's the right ballpark. So that would just give you a clue, are you even in the right place? Yeah, 1/2 the base times the height. That was my poor estimation of the height. Good deal. Any questions on that? All right, another applications of radicals. Okay, we've already done all that. Let's move on to 5.3. Okay. Taking forever for this thing to load. Okay. Start the slideshow from the current slide. All right, we're still doing Chapter 5, Exponents and Radicals. 5.3 is combining radicals and simplifying radicals that contain variables. Okay? This is sort of the next step. The last section gave you the tools you need to do this. So let's use those tools. We'll simplify expressions by combining radicals. It will simplify radicals that contain variables. Two different things here. Let's start here. Recalling our use of the distributive property as the basis for combining similar terms. Remember that? 3x plus 2x is pretty easy. 5x, of course. 8y minus 5y? 3y. 2/3 a squared plus 3/4 a squared. Yes, what's that? 12. How many twelfths is 2/3? 7 twelfths? I think it's a little bit more than that. Huh? 8. Okay. This would be, this is 9/12, that's 8/12. 9/12 plus 8/12 is 17/12 a squared. Perfect. All right. Finish you decided to come today. Good. Okay. Wondering where you were. Okay. Now, so, yeah, we know how to do that, right? Well, guess what? We do the same kind of thing with radicals. Only now it's not the like terms, it's like radicals. Okay? So, for instance, if you had 3√2 plus 5√2, guess what that would be? 8√2s, exactly, okay? If you had 2 times the cube root of 5 minus 3 times the cube root of 5, what would that be? times the cube root of 5. Perfect. Okay, uh-oh. Now we have 4 root 7 plus 5 root 7 plus 6 root 11 minus 2 root 11. What in the world would that be? 9 root 7, perfect. Plus 4 root 11, exactly. You can't combine x's and y's, neither can you combine root 7s and root 11s, okay? That's different routes. So, in order to be added or subtracted, radicals must have the same index, okay, and the same radicand. These two you can't combine, these two you can. Those two you can, okay? Thus, we cannot simplify an expression. If you have 5 root 2 plus 7 root 11, that's the simplest you can get. Leave it just like that. There's nothing you can do to simplify that any further. But if it's 5 root 2 plus 7 root 2, yes, you could do something with that. Good deal. And always, you use your rules. If you had any perfect squares hiding in there, simplify those first. Okay. So simplifying by combining radicals sometimes require that you first express the given radicals in simplest form, which is what I was just saying. Then apply the distributive property. And this following example illustrates that. Here we have 3 root 8 plus 2 root 18 minus 4 root 2. Now just glancing at that, say, boop, none of those are the same, so we can't simplify, right? First, let's simplify the radicals. Can we simplify root 8? Question. Yes, how? How can you simplify root 8? Square root of 8. That's the square root of what? 4 times the square root of 2. Exactly. Okay, how about root 18? The square root of 9 times of 2 again, minus 4 root 2. Can't simplify root 2. That's, oops, that's a 2, not a 7. Ugly, ugly, ugly. Okay. All right, let's get that simple. Looking nicer. Okay. What is root 4? 2. So 3 times 2 is 6 root 2 plus, what's root 9? 3. 2 times 3 is 6 root 2 minus 4 root 2. What would that be? Anyone? 6 plus 6 is? 12 minus 4 is? 8 root 2. 8 root 2. All right. Look at that. I think they got the same thing. Let's clear this out of the way. Any questions on that before I erase it? See what we did? What's that? I can't hear. Oh, the 6, okay. I skipped some steps, sorry. This is 3 times root 4. What is root 4? 2. 3 times 2 is 6. And over here, 2 times root 9. What is root 9? 3. 2 times 3 is 6 again. And then the root 2s, you didn't have anything more. Does that answer your question? Yeah, good deal. Okay. They may take a few more steps and not do it quite so fast as me. Let's see what they do. They wrote it all again. That's really worthwhile. Then they did the same thing we did. They broke the root 8 into root 4 times root 2. They broke the root 18 into root 9 times root 2, and then they left the 4 root 2 as it was. And then they probably put in one more step, which is probably useful. Yes, here they did. They said this is 3 times 2. Root of 4 is 2 times root 2 plus 2 times root 9 is 3 root 2 minus 4 root 2. And that gave them 6 root 2 plus 6 root 2 minus 4 root 2. And that was, okay, 6 plus 6 minus 4 times root 2, which is 8 root 2. Good deal. Everybody see that? Take as many steps as you need to so you can understand what you're doing. Don't take shortcuts if they confuse you. Take as many steps as it requires. Okay? There's no penalty for being more thorough. Okay? None whatsoever. So there was example 1. All right, they're skipping example 2 and 3. Let's go back and do 2 and 3. Simplify this. 1/4, we love fractions, times the square root of 45 plus 1/3 times the square root of 20. What would you do first? A little louder? No, you don't have to do anything with the fractions first. We'll do that later. What did someone say about square root? What is square root of 45? 9 times 5. So that would be the square root of 9 times the square root of 5. Plus 1/3. How about 20? Square root of 5 times the square root of 4. Perfect. What's the square root of 9? 3. So this will be 3/4 root 5. I can't write. Plus, what's the square root of 4? 2. So that'd be 2/3 root 5. And that's one we did, wasn't it? Not quite. I thought we did. Well, anyway, what is it? What you need is, now we need your denominators. No, you're making fun of my writing, aren't you? Okay. Those are both 5s. I just don't write very well. Okay. Let me try it again. It probably won't come out much better. Because that's a 5, that's a 5. Yeah, I'm making fun. I understand. I'm not hurt at all. No. Yeah, okay. So where do we go from here? This is just algebra. Say again? Yeah, okay. And what would be your new denominators? You won't need 20. That's a 3. She's still making fun of my writing. My word, I mean, listen to this. Okay. Picky, picky, picky. Okay. All right. Gotta find you. Seth, right? Okay. What's your least common denominator? Between 4 and 3? No. 3 won't go in the... Huh? No, not the 5s. The denominators. What's the least common denominator? 12. Okay. The root 5s stay right there. Those are like your variables. That is a 5 there. Okay. Now, how many 12ths is 3/4? 9 12ths. How about 2/3? 8 12ths. And what does that turn out being? Woo. 17 12ths root 5. Okay. Not a very pretty number, but that's it. There's no problem with having numbers in the denominator. You just can't have radicals in the denominator. That radical is not in the denominator. Good deal. And that's what they got, 17/12 root 5. Good for them. Any questions on that? That was example 2. Page 260, chapter 5, exponents and radicals, 5.3, combining radicals and simplifying radicals that contain variables. Now, for all who have come in since the beginning of class, please go back and listen to the YouTube video. It's not up there yet. It'll be up there sometime later today, probably. And listen to the beginning of class, because that's when I tell how we're going to wrap up the term, what we're doing Wednesday, what we're doing Monday, what we're doing after that, when your final, all that kind of stuff we talked about. All right, that was example 2. Move on to 3. Okay. All right, example 3, top of the page. Whoa, 5 times the cube root of 2 minus 2 times the cube root of 16 minus 6 times the cube root of 54. What in the world are we going to have to do with this? Those are all cube roots there, which is sort of good. Can you simplify cube root of 2? No. That's just going to be 5 times the cube root of 2. What's that? Yes, we can. How? Okay, it was a cube root of 4 is not a perfect. 4 is not a perfect cube. Huh? No, you're on the right track. You just chose the wrong factors. What's another factorization of 16? Yes, the cube root of 8 times the cube root of 2. Because 8 is a perfect cube. Minus 6 times now this may be one you might want to pull over to the side and do your prime factorization. Do you think you do, or can you do this one in your head? Want to do the prime factorization? What's that? You tell me how you want to approach it. Prime factorization or work on it? 9. Okay, 9's not a perfect cube.
Is that 54?
54 is right there. That's the number.
You gotta do another of the 9 times 6?
Okay. 9 times 6 would be 54, but neither 9 nor 6 is a perfect cube. So we need a different factorization that does give us a perfect cube. Think of your perfect cubes. Remember when I had you write those on the board? 1 through 10, square them, cube them, fourth them, all that kind of stuff. I say, get to know these, yes. 27. So this will be the cube root of 27 times the cube root of what? 2. Excellent. Okay, so this is 5 times the cube root of 2 minus, what's the cube root of 8? 2. So this is 2 times 2 is 4 root times the cube root of 2 minus, and what's the cube root of 27? 3. 6 times 3 is 18 times the cube root of 2. All right. This is going to be what? It will be negative, right? How much? Second? I'd say negative 17. Because 5 minus 4 is 1, right? And 1 minus 18 is minus 17, right? Okay. Minus 17 cube root of 2. Let's see what they got. Oh, look at that. They got it right too. Good for them. Negative 17 times the cube root of 2. All right. Now, we've already done example 1, so I'm going to step through that. And now we're moving to simplifying radicals that contain variables. Okay? Before we discuss the process of simplifying radicals that contain variables, there's one technicality we should call to your attention. Let's look at the examples to clarify the points. Let's consider the square root of x squared. Okay? If x were equal to 3, what would x squared be? If x equals 3, that'd be 9. What's the square root of 9? 3. That's great, right? But what if x were equal to negative 3? What's x squared? 9 again. Well, negative 3 times negative 3 is still 9. And square root of 9 would be 3. But here, what your x was is what you got out here. Here's what your x was. You got out something different. Okay? And therefore, what they're saying is, if x is greater than or equal to 0, then the square root of x squared is always x. If x is less than 0, in other words, a negative number, then the square root of x squared is minus x. Okay? Which is unfortunate. Okay? So what we're going to do to avoid that is this. Using concepts of absolute values, we can state for all real numbers that the square root of x squared is the absolute value of x. Whether that x is plus or minus, the absolute value is going to be the principal square root. Now consider this radical, the square root of x squared, x cubed. The square root of x cubed. X cubed could be negative, okay? And when x is negative, it is negative when x is negative, and then we'd have to restrict the x to non-negative real numbers, otherwise you can't take the square root of a negative number. So, thus we can write, if x is greater than or equal to 0, then this is true. What's that? Yeah, it's a lot of blah, blah, blah. Okay. The trouble is, when you have a negative x, you can cube a negative x, right? And it becomes a negative number, right? But you can't take the square root of a negative number. What they're getting at is what they're going to want to do in a few minutes is say this cube root of x, the square root of x cubed is the square root of x squared times the square root of x, right? Because x squared is x cubed is x squared times x. Just like we did before, we can take square roots of both of those. And most of the time we say the square root of x squared is just x. Okay? Now, that's true anytime x is greater than or equal to 0. Always. Okay? And what we're going to do here, and this is their little thing, I wish they had just started saying this. Finally, let's consider the cube root of x cubed. Well, that could be, if x is 2, then that's 2. If it's negative 2, it's negative 2. That is correct to say the cube root of x cubed is x, because the cube root undoes its cube. They just wipe each other out. For all real numbers, again, no absolute value sign is necessary. So here's what they're getting at. And they took forever to get here. The previous discussion indicates that technically, every radical expression involving radicals and variables in the radicand needs to be analyzed individually in terms of necessary restrictions imposed on the variable. Blah, 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 right? To help you gain experience with this skill, examples of problems discussed under further investigation in the problem set. We're not going to do that. For now, however, to avoid considering such restrictions on a problem-by-problem basis, we'll merely assume that all the variables represent positive real numbers. If all the variables are positive, you don't have to worry about absolute values, whether it's the square root of a negative number, because you don't have any negative numbers. So that's what we're going to do. I wish they had just said that at the beginning. Let's just assume all the variables are positive. That would have done it. Okay? So let's consider the process of simplifying radicals that contain variables in the radicand. Here are some examples. Ooh. All right. I know we don't have much time. I'm going to show you a way to do it. It may not be the quickest way, but it's certainly a way to do this. Okay? And I think you'll find this a pretty easy one. factor everything in sight. Make that the square root of 8 is, what's the smallest prime number going to 8? You know it. No, it's prime number. 2. 2 times what? You said it. 4. Is 4 a prime number? No. Smallest prime number will go into 4. 2 times what? 2. That is a prime number. X cubed is x times x times x. Now this is a long, gory way of doing it, but this is almost student-proof. In the Navy, we used to say you had to make something sailor-proof, so not even the sailors would screw it up. So here's what we do. What's your index here? 2. If you don't see an index, you understand it to be 2. So now you look at pairs. There's a pair, and there's a pair. It's almost like you're playing poker, right? Okay? Pull out the first pair, 2. Pull out the next pair, x. And then you're left with the square root of 2x. See how that works? Does it kind of make sense? Okay? Let's do the next one. Square root of 45. What's the smallest prime number that'll go into 45? I know 5 will go into it. 5 times what? 9. Is 9 a prime number? No. What's the smallest prime number will go into 9? 3 times 3. Is 3 a prime number? Yes. Okay. Times, what's x cubed? X times x times x. What's y to the 7th? Oh boy. Y times y times y times y times y times y times y. Okay, this is the long way to do it, folks, but it'll work if you'll do it this way. What's your index here? 2. So you look for pairs of number. There's a pair, there's a pair, there's a pair, there's a pair, and there's a pair. Right? So what do we pull out? A 3x y cubed. You got it. What's left? The square root of 5x y. Perfect. Y'all are good at this. You see it? Okay. Let's do the next one. The square root of, what's the smallest prime number will go into 180? All smaller than that. 3 will go into it. I'll write it down. 3 times what? 3 times what? A little louder? Did I hear 60? 60 is correct. Smallest prime number will go into 60. 2 times what? 30. Smallest prime number will go into 30. 2 times what? 15. Smallest prime number will go into 15. 3 times what? 5. Is 5 prime? Yes. Okay. And then we'll do A times A times A times A times B times B times B. What's your index? 2. So you look for pairs. There's a pair, and you got them out of order, but there's a pair, there's a pair, there's a pair, and there's a pair. No apples, all pair. No, I'm just kidding. Okay. What's 2 times 3? 6. How many A's? A squared. How many B's? Just the B, and then you got a square root of what's left? 5 what? B. Excellent. Way to go, team. We're out of time, but guess what we'll do with this one? Prime factorization, but then we look for triples, not pairs, triples. And any triple you find, pull it out. Right? So that's how we deal with that. Okay? Sorry we didn't have any time to do any further. If you'll hang on just for a moment, let me run get your quizzes because they should be right finished. I'll bring them right back up. I should have turned off that, but I'll.
He might.
All right, here's the quiz. Should be easy scores, right? Anyone else? All right. Remember, I need all your quizzes, all your tests completed before Wednesday. Not this one. You don't have to have this one going with. Hey, is that a paper you want me to give you? What? Oh, you want one of those? You need one of both? Huh? Wait just a second. Anyone else need one of these? Okay. Oh, okay. Okay, review sheets? Okay. Is that what all y'all are standing here for? A quiz. Okay. Melvin, did you get a quiz? Okay. Did you? All right, sorry about that. Did you get a quiz? Okay. Are y'all waiting for review sheets? Okay. I don't know if I have enough. Who else needs one? Now these, don't go. That's not all. Anyone else need a review sheet? Okay. Let me give you the answer key for the review sheets. Those who just got those. You want the answer keys? Okay, anyone else? Okay. And then the short answer part, here it is. Oh, you have that. Okay, anyone else need the short answer part? Okay, good deal. No, this is just for you to work on. It's like, you know, and bring it to class and ask questions, anything you don't know. Okay. Now, good deal. Thank you. The second test? Huh? First and second. Have you started either one of them?
I think I've started the first one.
Started the first one. Okay. You need the first one.
Yes, sir.
Okay, did you start it?
I hadn't started.
Okay.
Let's see.
Okay. Oops. Go deep enough. There we go. All right. I think the room right next door to us is open. And you'll need test 2 also?
I started this the first one.
Yeah, that's the first one.
I started the first one.
Oh, you started the first one. I'm sorry you said that. I forgot.
It's okay.
Okay, here, I'll take this out. Okay.
There it is.
There it is. Okay. you waiting for now?
The second test. This is second test.
No, that's the third quiz.
Okay, I got it.
Are you going? Okay, why don't you finish that one and then I'll give you the other one. Okay. Did you already get the quiz or you did? Okay. Okay. So I've got class coming up in here. Let me in the next door, I think.